So today we are going to discuss the potential energy stored in a stretched wire, right? In a stretched wire, okay? In a longitudinal case, we need to find out what is the potential energy is being stored, okay? And we know very well if we are calculating for any Young's modulus, okay? Young's modulus is working for the longitudinal case, okay? In that particular one, we know the formula y equal to stress upon strain, right? So what is stress? Stress is force upon area divided by strain. Okay, now here let us take a small change, that is, let us take the original length as capital L and the change in length is small l. Okay, instead of delta L, let me take it small l, because we are going to differentiate as well as integrate. Okay, so delta L will create some problem, okay, while differentiating in the notation case. Okay, that you can do, no matter. Okay, so Young's modulus formula is stress upon strain, that is force upon area, divided by strain, that is change in length, that is small l, divided by original length, that is capital L. Okay, so now this capital L, when it will go upside, you know it very well, it will go to the numerator side, it will become f into L divided by this a is already at the denominator, so this is a into L. Okay, so what is the thing? The thing is that we are going to obtain Young's modulus y equal to FL by A into L. Okay, generally this is what? Stress upon strain formula. Any modulus of elasticity is the formula that is indicating the ratio of stress upon strain. Okay, so now here, this is because of what? This Young's modulus calculation, or there is a change in length, is because of what? Because of the force that you have applied, right? So this is a wire, suppose this is a steel wire or iron wire or something else, and if you will apply the force, the deforming force, because of some weight, then only this wire's length is going to elongate. Okay, so if we want to find out the force, we can find out from this formula only. How can I will find how much force that I have applied? The force that I have applied is F. So what is F is equal to this A into L will go to this side and will be multiplied with Y, and capital L will be divided. Capital L is what? Capital L is the original length, right? So F equal to A into L into Y whole divided by L. So what is this indicating? After applying a force F, the length of the wire capital L is elongated to small l. Okay, is elongated to small l. Okay, now how can I will find out the potential energy, right? We cannot compress it, right? The wire we cannot compress, so obviously we have to go for a expansion case, and by expanding that one for a further distance of dl, I can find out how much energy is being restored. Okay, so I have to find it that one. Okay, what I have to do, I have to stress the wire. Okay, I have to stress the wire and I have to check how much potential energy is being achieved due to work done. Okay, if I am going to stretch a wire, previously the wire is this, if I will stress, the wire will become like this. Okay, if I will stress the wire, obviously I am doing some work on it. Okay, so now let the wire is further increased to dl. Okay, let a small distance is dl, small length is dl, it has increased up to dl, then the work done will become dw, is because I am doing a small work, so how can I will represent a small work? Dw. So dw is equal to force into displacement that I have done. So force is what? Just now we have found out through the Young's modulus formula, that is A into L into Y divided by capital L. This is what? This is force, and multiplied with dl. Right? Now, if I want to find out the total work done, or what I can say, total work done by small changes. Okay, small changes that I have made, dw. Like this I will do so many dw's. Okay, then if I will calculate okay, or if I will integrate these dWs, I can calculate the full work done on that particular wire, right? dW is a small work done. If I will integrate, then I will go for a full work done, right? So now integrating both sides. If I will integrate both sides, okay, what I am going to get, this is integration of dW, and integration of dW is going to give me the result W. Then this integration of ALY divided by L, as you can see here, which are the constants? The constants are A, capital L and Y. Okay, let me take outside A into Y into capital L. And what I need to integrate? I need to integrate only the respective terms. What are the respective terms? I need to integrate DL, okay, or I need to integrate L with respect to DL, right? So integration of L into DL. Okay, so integration of L into DL formula is what? L to the power 1 plus 1 divided by 1 plus 1. This is what? L2 divided by 2. L square divided by 2. So this integration is going to give me the result L square divided by 2. Okay, so this I can write it by this one, that is half into this 1 by 2. I am writing it in separately, half into y into a into L square divided by L. Okay, this representation only I am writing in a perfect manner, half into y into L square upon L. This also I can write it by using some different notation, that I can make this one as separate in order to find out this formula, okay, particular formula, because work done is going to give me the energy formula. Let me write down this one, half into y into L square by L, in a different manner, means the same formula in a different style, that is half into y into L by L. Okay, are you observing? Half into y, let me write down here so that you will not be confused. Half into y into a, L square by L, half into y into a, L square divided by L. Okay, so this is the thing that I am going to write. So if I am going to write this L square, let me write it as half into y into, as usual, okay, L square upon L, let me write it as L by L, okay, L upon L, okay, and this side I will write multiply and divide by L, because I need to find out the formula, okay, a separate formula for it, okay. L upon L, instead of L square I will write one L upon L, another one is L upon L, and multiplied with A, and I have to eliminate one capital L, because there are not two L square, right? This is not a L square, this is only a single L, right? So L and L is present, so that means I need to multiply with another L. Now my notation of this one is equal to this one. Why I am writing, you will get to know in this step, okay. Now this y into L is known as what? Stress. How? Because y equal to stress upon strain. So y into strain, this strain will go to this side and it will be multiplied with y. What it is going to give me? It is going to give me the result of stress. I think you are observing here. Y equal to Young's modulus equal to stress upon strain. So y into strain, this strain will go this side, and if it is been multiplied, what it is going to give me the result? Stress. So y into strain is equal to stress. Okay, so strain is what? Strain is change in length divided by original length, L upon L. So y into L upon L is going to give me the answer stress. Okay, y into L upon L, just putting the formula of strain, y into L upon L is going to give me the result of stress. See here, see all of you, you can see here y into L upon capital L is going to give you the result of stress, right? So this is half into stress. Now coming back to this formula, what is this L by L? Change in length upon original length. This is what? Strain. Strain. Right? Now what is A into L? Area into length. That is volume of the wire. So what is the formula for energy or work done? If you will do the work, obviously you are going to achieve the energy. So work done or energy formula is what? Half into stress into strain into volume of the wire. Now if you will think that why we have wrote this one, because this is a common question that is being asked. Okay, what is the relation of energy with stress and strain? Then you have to represent with this one. This is a 3-mark long question. Okay, now if you will think that if you will write this formula, then you will get the mark or not, then obviously this is correct for some numericals. Okay, if this data is given half into y into a into l square by l, if you will write the work done formula or energy formula, you will also calculate the numericals. Okay, no problem at all, because as we need to find out the relation between the energy and stress, strain and volume, that's why we have expressed this one like this, or we have represented this one in different form. Okay, and after that we found out the energy expression as half into stress into strain into volume of the wire. Okay, now if I will find out potential energy per unit volume, okay, potential energy per unit volume, this is what energy exactly? Potential energy, because it is being stored in the wire if you will do the work, right? So potential energy stored in the wire is nothing per unit volume means what? The volume will be divided here per unit volume. So this volume and this volume will be cancelled. So what is the answer? Half into stress into strain. So the answer is half into stress into strain. Okay, understood everyone? Say me yes if you understood. Okay, so now moving on, Poisson's ratio. Okay, so this is one ratio, the scientist has given this one. Okay, Poisson's ratio is what? The ratio of the lateral strain to that of the longitudinal strain is called as the Poisson ratio. See, lateral is what? If there is a expansion or contradiction, compression in the lateral side, then it is known as the lateral strain. Okay, and longitudinal means you know it very well. Okay, along the lengthwise. Okay, so now let us find out what is Poisson's ratio. Again, the ratio of the lateral strain to that of the longitudinal strain is called the Poisson's ratio. See, this is the original length of the wire. Let me draw the bigger one. Yes, as you can see here, this is the original length of the wire. Okay, now after you will place a weight on it, okay, if you will provide some load on it, now it is going to be elongated in this direction. Okay, after elongation, how much it will become? This side, the diameter will be compressed. If you are going to stretch a wire, obviously its diameter is going to be compressed. So what will happen? The structure will become like this. Okay, this will be elongated. See, this to this as delta L, only this portion is the delta L. This is the elongation in the length. Okay, this is elongation in the length, and also the diameter is being reduced. What was the previous diameter? This is the previous diameter, original diameter, capital D. Now it has compressed to a diameter delta D. Okay, so now lateral side, what is the change, or what you can say, what is the strain? This is obviously Poisson's ratio is a strain ratio. Okay, so what is the change in the diameter section? That is change in diameter to that of original diameter delta D by D. See, delta D by D. This is for what? Lateral section, because the Poisson's ratio is telling us what? The ratio of the lateral strain to that of the longitudinal strain. Lateral strain is what? Delta D by D. Okay, and the longitudinal one is what? Change in length is delta L and original length is L, so delta L by L. Okay, so this is delta d by d is lateral divided by longitudinal strain. Okay, so the formula is what? Delta d by d divided by delta L by L. Okay, now all of you switch on your mic and say me yes if you understood up to this. Okay, so now we are going to compute some numericals. Get ready with your pen and paper. Okay, so now next is the numerical from the bulk modulus problem. Okay, this is NCRT numerical. As you can see, it is being represented here. The question is, compute the bulk modulus of water from the following data. Okay, compute the bulk modulus of the water from the following data. What is that? Bulk modulus obviously belongs with the volume, right? As you can see your notes, you can find it out easily. Initial volume of water is 1000 liter. Pressure increase 100 atm. Final volume is 100.5. Okay, 100.5 liter. Okay, and you can see here 1 atmospheric pressure atm. Okay, 1 atm, okay, is equal to 1.013 into 10 to the power 5 pascal. Okay, 1 atmospheric pressure atm is given as 1.013 into 10 to the power 5 pascal, right? Here we have given data like this. You can write it down quickly. What are the given data? Pressure is given to you. Pressure is what? Your pressure is P is equal to 100 atm, given in the question, 100 atm. Okay, so 1 atm is this much. 100 atm is equal to 100 into 1.013 into 10 to the power 5. Okay, 10 to the power 5 pascal. Okay, this much. Okay, so this is the pressure data is given to me. Okay, another data is what given to me, that is initial volume. Okay, let me write it as V. V is given, how much V? V is given 100 liter. Okay, liter means we need to convert to a what you can say feasible unit. Liter, let me convert it to meter. So liter is equal to 100 into divided by 1000. Okay, so it will be 10 to the power minus 3 meter cube. Okay, so volume of the first one, initial volume is 100 liter, that is 100 into 10 to the power minus 3 meter cube. Shall I rub? Okay, now what is the final volume? Final volume is also given. Let me represent with V dash. V dash is equal to 100.5 liter. 100.5 liter. Again you can write it as 100.5 into 10 to the power minus 3 liter. Meter cube. Okay, meter cube. Okay, so now let us find increase in the volume. Okay, let us find how much it has increased, because we need to find delta V, right? So how much it has increased in volume, let us find out the difference, how much changes taken place. Okay, so delta V is equal to obviously final minus of initial, V dash minus of V. So what is V dash minus of V? V dash is 100.5 and V is 100, and what thing is common? Into 10 to the power 3 is common. Okay, 10 to the power minus 3 is common. Okay, so we can write it as, if we will solve, 100.5 minus of 100 will give you 0.5, obviously 0.5 into 10 to the power minus 3 meter cube. Okay, this is delta V. Shall I rub? Okay, so now here we will go for the bulk modulus formula, B formula. So the B formula is Who can say what is the B formula? Stress upon strain, right? Stress was what? Force upon area, okay, divided by how much changes were taking place? Delta V upon V. Yes, this is the formula. Change in volume to that of original volume, right? So now I can write it as F by A into B by delta V, because V will go this side and it will be multiplied. So B by delta V. So F by A, can you represent this one? This F by A is nothing but pressure. Okay, force and area, no data is given to us. Now you have to apply the common sense, what I have to interchange with it. So force upon area is pressure multiplied with V by delta V. V by delta V. This is the formula right now for the bulk modulus. This is another formula. P into V by delta V. Okay. Shall I rub? Anyone? Okay, so now let me place the values. Okay, B is equal to PV by delta V. P is how much? Pressure 100, okay, into 1.013 into 10 to the power 5, okay, multiplied with V. V is the initial volume. What is the initial volume? 100 into 10 to the power minus 3. You can see the given data, whole divided by delta V. Delta V is how much? 0.5 into 10 to the power minus 3. So if you will solve, you will get the answer in Pascal, that is 2.026 into 10 to the power 9 Pascal. 2.026 into 10 to the power 9 Pascal. This is the answer. Okay, so shall I rub? Simultaneously you people write yes or no? Okay, okay, so let us solve another numerical, that is a square lead slab, okay, a square lead slab of side 50 centimeters. So 50 centimeter is there, I have to convert into meter, of side 50 centimeter and thickness 5 centimeter is subjected to a shearing force, okay, is subjected to a shearing force. Shearing force is same as that of your tangential force, and because of the tangential force there is a shifting in the rigid surface is being taking place. Okay, if you can check the previous note you can find out. Okay, on its narrow face, okay, on its narrow face of magnitude, okay, of magnitude 9 into 10 to the power 4 Newton, of magnitude 9 into 10 to the power 4 Newton. The lower edge is riveted to the floor, okay, the lower edge of the square is riveted to the floor, okay, the square is like this, okay, this is being riveted to the floor. Okay, how much is the upper edge displaced? Means that is asking how much is the upper edge is going to be displaced. Okay, and here it has given shear modulus is given 5.6 into 10 to the power 9 Pascal. Okay, shear modulus, let us represent with eta symbol. Shear modulus is given, already we have found out the formula. Shear modulus, that is given 5.6 into 10 to the power 9 Pascal, right? So first let me draw the diagram first. Okay, all of you draw it and you will get to know how it will take place. See here, this is a square box like this, okay, riveted to the floor. Okay, after you will apply a force in this direction force, it is going to shift. Okay, now this angle is what? Theta. And shearing strain, or you can say shearing strain, is going to be found out by this angle theta only. Okay, by this angle theta. So how much it is being expanded in the width side? You can say this is what my, this is delta L. Okay, this delta L is the change in, what you can say, width. Okay, change in width, and theta is the angle right now. Okay, so now let us write down. All of you drawn, I think so? Yes or no? Okay, so now let us write the given data. What are the given data here? The given data is L equal to 50 centimeter. Okay, so I need to convert it. It will give me how much meter? It will give us 0.5 meter. Okay, force is given 9 into 10 to the power 4. Okay, shearing force is being applied 9 into 10 to the power 4 Newton. Okay, now next is what? Eta, that is the shearing modulus. Okay, shear modulus is given 5.6 into 10 to the power 9 Pascal. 5.6 into 10 to the power 9 Pascal. Okay, now here I need to find out what? Obviously the area, right? I can find out because stress formula divided by strain, this will give me the answer, right? So stress is what? Force upon area, right? So area I need to find. So area is equal to what into what? You have given here 50 centimeter of the side, okay, multiplied with thickness of 5. So what should be the area? 50 into thickness. So 50 into 5 will give you 250 centimeter square is your area. So 250 centimeter square is how much meter square? Is nothing but 250 into 10 to the power minus 4 meter square. Okay, 250 into 10 to the power minus 4 meter square. So shall I rub? Okay, so now this one will become, the formula will become eta is equal to, normal formula I am writing, F by A divided by delta L by L. Okay, so this will become F by A into L by delta L. Okay, now we will place the formula. Okay, what we need to find? We need to find how much is delta L, because in the question it is asked how much is the upper edge displaced. So upper edge displacement was what? Delta L. That's why I need to find. Okay, so delta L will go to this side, eta will come to this side. Okay, so just a small interchange in the formula and we can find out easily. Okay, so let me write down the formula again. The formula I can write it as delta L is equal to F by A into L by of eta. Okay, F by A into L by of eta. Now place it. Okay, so here I can place it as 9 into 10 to the power 4 into 0.5 is the length, area 250 into 10 to the power minus 4 multiplied with eta. Eta is given, shear modulus 5.6 into 10 to the power 9. Okay, getting my point? So this will be 5.6 into 10 to the power of 9. Okay, so the answer will coming as, all of you write down, this will be the answer 3.214 into 10 to the power minus 4 meter. Okay, so the answer is 3.214 into 10 to the power minus 4 meter. Okay, so shall I rub? Okay, so this is one of the answer. In the next class we will find out how to find out theta. That is also another question. Don't worry. Here, as it has asked for elongation delta L, that's why we represented with the common formula. Okay, now the next question is a metallic cube whose each side is 10 centimeter. As you can see in the question, a metallic cube whose each side is 10 centimeter is subjected to a shearing force, again 100 kgf. This 100 kgf is 100 into 9.8 Newton. Okay, how to convert it to Newton? Because the formula are in Newton, right? So 100 kgf is 100 into 9.8, this much Newton. Okay, the top face is displaced through 0.25 centimeter. Okay, the top face is displaced. See, displaced means it has given us how much it is being changed. Okay, displaced up to delta L is given to us 0.25. The only thing in this numerical section is you have to identify. Okay, so delta L is given, that is 0.25. Write it simultaneously. With respect to the bottom, calculate the shearing stress, strain and shear modulus. It is asking us what is the shearing stress, strain and shear modulus. Shearing stress or any stress has the same formula, force upon area, right? So here let us move on how to find out the answer. So all the given data is given to us. So now length I have written 10 centimeter is given. You need to obviously convert to meter. So how much meter it will become? 10 upon 100, 0.10 meter. Force already I have wrote 100 into 9.8 Newton. Delta L, okay, delta L equal to 0.25 centimeter. This one you can write it as divided by 100. So this will be 0.25 into 10 to the power minus 2 meter. Okay, now the first question is what is the shearing stress? Okay, so write down all of you, shearing stress, SHEARING, shearing stress. Any stress has the formula of force upon area. Okay, now the area is what here? Is having a side of 10 centimeter, length square. Okay, F by L square. Okay, F by L square. Getting? So this will be 100 into 9.8 divided by L square. L square is 0.10 into 0.10. 0.10 into 0.10. So this will give you the answer 9.8 into 10 to the power 4. Calculate it with the help of your calculator in the home. Okay, 9.8 into 10 to the power 4, 10 to the power 4 Newton per meter square. Newton per meter square. This is the shearing stress. Hope all of you wrote. Now next one is shearing strain. Okay, strain has the formula, you know it very well. What is that? Delta L upon L. Okay, so delta L upon L, write down shearing strain, delta L upon L, that is 0.25 into 10 to the power minus 2, this is the delta L, divided by 0.10, right? So if you will place, you will get the answer. This shearing strain is what? Theta. Okay,